Hello, 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 class. Today we are going to do, if I can get the pin to work, 11.5. And 11.5 is modification of member stiffness. So if you recall, we were looking at moment distribution. And moment distribution takes the fixed in moments for each member with a load applied to it, and then locks it in, releases it, and then based on the stiffness, distributes that load throughout the structure. Okay, and this is all based on our slope deflection equation. Near, far, and it's equal to 2EI over L times 2 theta near plus theta far minus 3 psi in near and far plus the fixed end moments, near or far. Okay, depending on which one you're looking at. Okay, so what we want to do is look at, I said last week that our fixed end moments were going to be distributed based on the member stiffness, and the member stiffness is represented by this guy, our relative flexural stiffness. Okay, so the key term here is the relative flexural stiffness. Now, if you can get the absolute flexural stiffness, then you're not going to have to be doing so many carryover, fixed end moment, distributed end moments, carryover, distributed end moments, and carrying it over. So what you want to do is figure out what the effect of end conditions are on the flexural stiffness. Okay, so what we want to do is take this equation and let's apply it to this guy. Let's move this guy up. And take that. Okay, we'll come back to this. Do that. Okay, so we have a roller and a fixed end here. Okay, so what we want to do is determine the absolute flexural stiffness. Okay, the absolute stiffness at this joint and at this joint. This joint's going to be easy, right? Because we know what the rotation is. But we want to figure out what is the maximum, or what is the MAB, the moment equation for this configuration. So the moment here. So what we do is we look at MAB using our slope deflection equation is going to be, 2EI over L plus 2 theta A. Let's get rid of this. Plus theta B minus 3 psi AB plus FEM. Okay, so right now all we're doing is figuring out what is the stiffness right here. So in this case, our fixed end moment is going to be equal to 0. We know that we're going to apply a unit rotation at theta A. So that this theta A is just going to be a unit rotation. And then what we're doing is figuring out what is the moment at that location when we just apply a unit rotation. We know what our theta B is. What is it? I can't hear you. It's equal to 0. Okay? So our theta B is equal to 0. There's no relative displacement. So our psi AB is going to be equal to 0. So we can figure out that our moment at A is going to be equal to 2EI over L times 2 theta A is equal to 1 plus theta B is equal to 0 minus 0. And then we have no load on it, so we have no fixed end moment. So therefore, our moment at A is equal to 4EI over L. Okay, so this represents now, this is our absolute flexural stiffness. Okay. Okay, so now let's say we have a beam with a roller on one end and a pin on the other. And what we want to do with this guy is let's apply a unit rotation. This is A, this is B. We're going to apply a unit rotation so that we have a deflected shape. It's not a very good deflected shape. Like this, such that we have a unit rotation. This is going to be our theta A. And we want to find out what the moment at this end is going to be. Okay, so we're going to use our equation again. Theta A is going to be equal to 1. Okay, and now when we have a roller and we apply a unit rotation, we have a theta A equal to 1. When you have a pin at the other end, if you refer to figure 9.3E, the relationship between a roller and a pin, if the rotation is equal to 1 at A, the rotation at B is going to be half of that in the opposite direction. So this theta B is equal to half. And we can just say half because we just said theta A is equal to 1. Okay? And again, here, because we have no load, our FEM AB is FEM BA, and that's equal to 0. We also have no relative displacement at the joints, so our psi AB is also equal to 0. So now let's plug this into our slope deflection equation. MAB is equal to 2EI over L times 2 theta A plus theta B minus 3 psi AB plus FEM. And this guy is 0. Let's change colors. This is 0. This is 0. This is equal to 2EI over L times 2 times 1. This I said is a half, so this is minus 1/2. So that we have, oops, this is equal to 3, because this ends up being 1.5 EI over L. So this is going to reduce the amount of times that you're going to have to do the carryover and distribute to your ends. Okay, so what this tells you is that a beam that is loaded by a moment at one end whose far end is pinned is 3/4 as stiff as the rotation with the same as the rotation on a beam with the same members, but it is fixed at the other end. So that makes sense, right? So if we come up to here, let's look back at this guy. When it's fixed, it's 4 EI over L. So this is your absolute flexural stiffness. That's the moment here is going to be equal to 4 EI over L. And then here, the moment when you have this rotation is only going to be 3 EI over L. Okay? So it's that's how much this is not the moment that's going to occur. This is the moment that it takes to cause a unit rotation. Moment required to cause, that out of there. Oh. Unit rotation for roller pin. And then this one is moment required to cause unit rotation for roller fixed. Okay, so hopefully that makes sense, because this guy is going to be stiffer, it's going to be harder. This is taking up more, this is resisting more, it's not allowing this rotation, this at B to rotate when you apply this rotation, so it's resisting it, so it's going to take you more of a moment to rotate it 1 unit than it will for a roller and a pin. Okay, and so this, notice, I want you to notice that this is also illustrated in figure 11.12b, where it gives you that moment that's required to cause a unit rotation. And up here, this one is in figure 11.12a. Okay, so let's go to the next one. Let's go to the next one. So I'm not going to walk through all these because you guys can play this back. But for a moment in double curvature, what would you expect? If you were causing double curvature and it's going to be symmetric, a pin and a roller, if you're rotating it, a unit rotation here, and you're going to have a unit rotation here. So to get it in double curvature, obviously they're going in the opposite direction. There's no loads on here. So looking at this fixed end moment's going to be 0. You've got 2 theta A plus theta B. There's no low or no relative displacement on here, so that you end up having 2 plus 1 is 3. These are both equal to 1. And this is going to take 6 EI to cause a unit rotation in both directions for double curvature. So then it's going to take 50% times 50, it's 50% greater. The stiffness to bend in double curvature is 50% greater than with the far end fixed. Okay? Now, if we want to say we want to cause a unit rotation at both joints, so if you've got pin, and a roller, and you want to cause a unit rotation at both joints, but in the opposite direction, so this is because of this is single curvature, right? Because you've got one going one way, one going the other way, so that you end up with 2, and again, no relative displacement, no loads applied, and all we're doing is no loads applied because we just want to check the stiffness. So this is going to give us 2 times 1 minus 1. That ends up being 1, so you end up with 2 EI for a rotation of A equal 1 and rotation at B equal to -1. Okay, so therefore, let's move this down a little bit so you can read it. In single curvature, half the stiffness of fixed, single curvature I should say, with thetas both equal to 1, it's half the stiffness of the far end fixed, and it's 1/3 of the stiffness of double curvature. Okay? Okay, so the last 2 sections that we want to go over for moment distribution are side sway from loaded joint and then side sway due to member loads. So if we look at a structure that is free to sway, but still stable, so you're going to have a fixed section here. This guy is fixed. And then this side has a pin on it. So if we are going to apply a load that's going to give a unit displacement, this displacement here is going to be equal to the displacement here. We don't have any fixed end moments from the joint load, so because it's a load on the joint, correct? We don't have any fixed end moments, but we know that there's going to be moments. There has to be moments in here because it's displacing and it's curving. You have curvature in the member. Okay, so we can say that this is going to apply as long as we are in the linear elastic material range. So as long as we're in the linear elastic material range, we can say P1 and P2 are going to be equal. I have it backwards, but it doesn't matter. And your displacements, θ1 and θ2, the relationship between the displacement and the force is going to be equal. I shouldn't say P1 and P2 are equal. The relationship between the two are equal. Okay? And so what that means, P1 and P2 aren't equal, but you've got a load, whoops, you've got a load P1, so if this is your curve, say this is a curve for steel, correct? So a curve for steel, you've got a load P1, you come on here, you're in the linear elastic range. So this range right here is your linear elastic range. So as long as you're in that linear elastic range, the delta 1 that corresponds with your P1, the ratio of those is going to be equal to the ratio of your P2 over the delta 2. And this, again, is within the elastic range of the material. Okay, so if we say that our delta here is just a unit displacement, let's solve for that unit displacement. Our thetas, if we're fixed, okay, because we want to do fixed in moments, we're fixed. So for a fixed member with no unit loads, the rotation at that joint is going to be equal to 0. So it's going to be equal to 0 here and equal to 0 here. I'm pointing to at A and at B. Okay, your translation, your relative displacement, is going to be equal to the unit displacement that we have over the length. So in this case, we have delta over L, and delta is just equal to 1. So this is going to be over L, and it's minus 3. Our thetas are equal to 0, and our fixed end moment is equal to 0 as well, because it's a joint load. Whoops, 0. Joint load. But again, that doesn't mean that we have no moment in the member, because we have curvature in the member. So our moment, AB, is equal to 2EI over L times -3, because this is the only term. This went to 0, and this went to 0. This is the only term that's left in the equation. It's a -3 delta over L. That delta is equal to 1, so we end up with -6 EI over L squared. And so this is for sideways, this is the equation, the stiffness for side sway due to a load at a joint. All right, so for the steps is you apply a unit displacement, you lock the structure, clamp it, and calculate your displaced member end moments. Then you remove the clamps and you distribute the moments. You solve for the applied load from the free body diagrams and moments and shears, and S is a load that corresponds with delta equal to 1. All right, and then you step 4, this says step 4, gives the shear and moment for S, and then to get for the load S that you're applying here, and to get M and V for P values, multiply the M and V diagrams that you get by P over S. Okay, so you solve for S, and then you multiply by the actual load over the ratio of the S that you did apply. Okay, so using that last technique, that last analysis, we're going to apply that in superposition to side sway due to member loads. Okay, so we talked about if you have a member load here, or you have a member load that's not symmetric, or your boundary conditions are not symmetric, that you're going to get side sway. Okay, so what we're going to do is, this is going to be similar to our virtual loads where we apply and use superposition. So what we'll do is, if we've got this unbalanced load, we're going to restrain it and then analyze as if there's no side sway. And then we're going to remove these loads. Let's not cross that out. But what we'll do is not have those loads, but then analyze with the side sway at a joint, because previously with this one you had this load. Whoops, I want that to be that color. This is the load that you analyzed with these, and then you took and removed that joint and said, what is the load that's that reaction, the side sway that reaction causes? And then you use superposition to combine them. And so we talked about this also last week a little bit. How in the world do we do moment distribution with a frame? It gets all crazy. So what I like to do is to take it, if we have a simple beam like, or a simple frame like this, I'll just take it and sort of stretch it out so that I can, not stretch it out, rotate it about this point so that I can just carry on and do my moment distribution from these locations. Okay, and so then from there you go and you find your fixed end moment from AB, from BC, and from CD, and vice versa, correct? Okay, so for practice, what I'd like to see you do, let's use green. is work problem 11.11. And 11.11 looks like this. I'll let you look it up. P is equal to 30 kips. 30 kips. And this is 2 kips per foot. Okay, so y'all should look at this and say, that is indeterminate. Even though I didn't give you the dimensions on this, it is symmetric. So this means no side sway. And the way I want you to take this is to do just like what I showed you. Whoops. And then break it out into just a fix like this, where you've got A, B, and C, and D. And because I said it's indeterminate, you need to use some sort of indeterminate solution process. So take it and just analyze it like this, just to get practice with analyzing a frame with moment distribution. Practice with moment distribution for frames. Okay, so I know on the schedule I had said that we were going to go over the test, but I'm not done grading them all, so Friday we will go through the test, and that's about all I have for you today. Short day, but I will have this posted. This lecture will be posted on Moodle. I'll send you, or I'll put a link on Moodle, and the lecture will be posted on YouTube. So I'll give you a link to that. I hope you guys have a good week, and I will talk to you Friday.